Problem 8.51, which is going to be the step response of a series RLC circuit with just a little bit more circuit analysis involved. In this one, you kind of have to look at the circuit before switching over here, and then the circuit after switching to the right. So in the circuit before switching is going to help you figure out some of your initial conditions, and importantly, what we want with initial conditions is the voltage across a capacitor and the current on an inductor. We can see pretty easily here that the initial current on the inductor, the 5 millihenry inductor, is going to be 0 because there's an open circuit at t less than 0. So 0 amps. The voltage on our capacitor we can figure out by looking at the circuit kind of here on the left when the switch is in position A, and essentially it says that the switch has been closed for a long time, so we can assume that the circuit is operating in like the steady state out of transient time. So the capacitor will be fully charged and there'll be no more current flowing across it, meaning we can look at just this right here to determine the voltage across the capacitor. And essentially all that is the series combination of a 9 kilo ohm and a 15 kilo ohm resistor is 24 kilo ohms. And then to find the current in that loop here, like this, we're just going to do 80 divided by 24,000, which is roughly 0.003333 amps. And now 15 kilo ohms times this current is going to be 50. And because the capacitor and the 15 kilo ohm resistor are in parallel, the voltage drop across them will be the same. So that means we know that initially our capacitor is going to have 50 volts across it. So that's our other important initial condition. And we know that the resistance for our series RLC circuit is 100 ohms. We've got that. Okay, so once you've found out the initial conditions that we care about, we think about the circuit switching into this position, position B, where we now have we're now going to have the step response of a series RLC circuit. And we know it's a step response because in the final circuit there's a 100 volt source involved. So the first thing that we're going to do, because we already have all of our relevant initial conditions, is find our Neper frequency, which for a series RLC circuit is R over 2L. So you have 100 over 2 times 0.005 henries, which is equal to 10,000 radians per second. For our resonant frequency, 1 over LC, omega squared is 1 over LC, have 1 over 0.005 times 2 microfarads, so 2 times 10 to the negative 6 farads, which is equal to 100 million radians per second. And now you'll see that if we make our comparison here to figure out the type of response, alpha squared compared to omega squared, alpha squared is also equal to 100 million, because that is 10,000 squared. So in the case that we have alpha squared and omega squared are equal to each other, this is a critically damped response. So as with underdamped responses, we don't actually need to calculate our S1 and S2 values, because we can essentially solve everything we need to solve with just our alpha value, and then we can find our D1 and D2 solutions. But before we move on to that, we also need to find the final voltage across the capacitor, and that's pretty easy, because we can see that we have a 100 volt source here. So once this has been closed for a long time, and it has discharged its original 50 volts, or been compensated, it'll come up to this value of the 100 volts, and so V final is going to be equal to 100 volts. And now we can go ahead and move on. So we've already calculated alpha, and our equations here are going to be V final plus D2 is equal to V initial. And so that's going to be pretty simple to solve. We have 100 plus D2 is equal to 50. So our D2 value is going to be negative 50, and that's one of our that's one of our coefficients. And then the second equation for finding our other coefficient, D1, is D1 minus alpha D2 is equal to I naught over C, because this is a step response. So we already have D2, and we already have alpha. And our I naught is 0, so makes the problem pretty simple for us. Alpha is 10,000. D2 is negative 50. And then I naught is, as we said, it's 0 amps. So anything over, or 0 over anything is 0, so this all gets set equal to 0. So D1 is equal to, so let me calculate that, 10,000 times 50, which is 500,000, I believe. Yep. So that's going to be positive 500,000, and then we subtract it over. So this is negative 500,000. And now we have all of the information that we need to construct our equation for voltage across the capacitor. And for the case of a critically damped response, voltage across the capacitor is equal to V final plus D1 T e to the negative alpha t plus D2 e to the negative alpha t. And the reason for this extra t here is because in the case of critical damping, your alpha and omega values are the same. So what you have there is referred to as a repeated root, and we need to have this t in here to make the solution to the differential equation work, essentially. And so let's just go ahead and build out our solution here. VC is equal to, what did we say? V final was 100 volts. 100 volts. And our D1 value is negative 500,000. So we've got negative 500,000 T e to the negative 10,000 T. Our D2 is negative 50, I believe. Well, yeah, negative 50. Negative 50 e to the alpha. Yeah, that's correct, but we need the actual number. To the 10,000 T. And of course this is in volts. And now we have the equation for voltage across the capacitor, but if you wanted to find the equation for current, because typically in series RLC circuits we like to look at current going through all of our different components, you can pretty easily find that by solving I is equal to C dVC over dt. So essentially all we would do is take the derivative of this equation, multiply it by our capacitor value, and that would give you the equation for I.